When you multiply by a weight matrix W, you are not just computing dot products. You are applying a linear transformation, rotating and stretching the entire feature space into a new geometry. Every forward pass through a neural network layer is a linear transformation followed by a non-linearity. Today we make this precise. Linear maps, their kernel and image, the rank-nullity theorem, and orthogonal projections. These tools explain why low-rank weight matrices lose information, how attention projects queries onto key subspaces, and why least squares regression is literally a projection. A transformation T from V to W is linear if it satisfies two properties. Additive T of U plus V equals T of U plus T of versus homogeneity, T of C times V equals C times T of versus both together. Every linear transformation can be represented by a matrix A such that T of X equals A times X. To find that matrix, compute where A sends each standard basis vector. The jth column of A is T of Ej. 6 geometric types: scaling, rotation, reflection, shear, projection, and identity. Composition of two linear maps is matrix multiplication. T followed by S equals B times A times X. Two subspaces every transformation creates. The kernel, also called the null space, is all vectors V such that T of versus equals 0. It is a subspace of the input space V, always containing 0. Its dimension is the nullity of T. The image, also called the column space, is all possible outputs T of V as V ranges over V. It is a subspace of the output space W. Its dimension is the rank of T. The rank-nullity theorem: rank plus nullity equals n, the input dimension. This is fundamental if your weight matrix maps 512-dimensional input to 64-dimensional output. Rank 64 means nullity 448, that many input directions are destroyed. Compute null space with Skippy. Lena LG, null underscore space, rank with NP, Lena LG, matrix underscore rank. Orthogonal projection is the geometric operation that minimizes distance. The orthogonal projection onto the column space of A is P equals A times the inverse of A transpose A times A transpose. This matrix satisfies two key properties: P squared equals P, called idempotency, and P transpose equals P, called symmetry. The projected vector Pb is the closest point in col A to B. The error vector B minus Pb is perpendicular to col A. This is exactly least squares. The normal equations A transpose A times X hat equals A transpose B come from requiring the error to be orthogonal to col A. For an orthonormal basis Q, the projection simplifies to Q times Q transpose. Build P with NP, outer for a unit vector, or Q at Qt for the orthonormal case. 4 applications. 1. Each weight matrix W in a neural network layer defines TW from Rn to Rm. The null space of W is the set of inputs the layer cannot distinguish. Low-rank weight matrices intentionally project to lower-dimensional subspaces. This is the foundation of parameter-efficient fine-tuning and LoRa. 2. In transformers, the projection matrices WQ, WK, WV are linear transformations from D model to DK. The attention score is a dot product in the projected subspace. 3. PCA applies the orthogonal projection P equals QK transpose, where QK contains the top k eigenvectors of the covariance matrix. 4. For 96,000 device monitoring, the rank K approximation defines a transformation Tk that maps the full metric space through a k-dimensional bottleneck. Residual projection norms flag anomalies. 4 facts cold. 1. T linear IFF additivity and homogeneity. 2. Every linear T equals A times X for some matrix A3, rank plus nullity equals N always. 4. Orthogonal projection P satisfies P squared equals P and P transpose equals P. Exercise 1. For A equals 1, 2, 2, 4, compute rank it is 1. Find the null space vector it is any multiple of 2, 1. Verify rank plus nullity equals 2. Exercise 2. Build an orthogonal projection P onto the line spanned by U equals 1, 1, 0, divided by root 2. Verify idempotency and symmetry numerically. Module 2 is complete. 9 videos. You started with vectors and dot products and finished with linear transformations and orthogonal projections. You now have the complete linear algebra toolkit, geometry, matrix operations, eigenstructure, SVD, vector spaces, and transformations. Module 3 is probability and statistics, the language your loss functions speak. Every gradient, every likelihood, every regularizer has probability theory underneath it. Video 18 starts Module 3 with random variables and distributions. Subscribe so Module 3 is ready. Drop your biggest Module 2 insight in the comments. See you in Video 18 and Module 3.